Hello guys, we are group 2 from section 3. These are our group mates who are Chong Hee-feng, Lai Yong-juang, Gan Ji-hen and William Gans. We are required to design a flash column for separating binary mixture of benzene and hexane. The name flash originates from the fact that a liquid at a pressure equals to or greater than its bubble point pressure flashes or partially evaporates when the pressure is reduced below its bubble point pressure, producing a two-phase system of vapor and liquid in equilibrium. In this group project, P and T flash are considered, which refers to any calculation of quantities and compositions of the vapor and liquid phase, making up a two-phase system in thermodynamic equilibrium at known temperature, pressure, and overall composition of inlet stream to the flash. Based on scientific research, the typical temperature used for the flash separation process is around 80 degrees Celsius, and pressure is found to be around 120 kilopascal for most realistic cases. Moreover, based on some other research paper, the usual initial overall composition of inlet mixer solution into the flash column is assumed to be in equimolar, where Z1 is equal to 0.5, which is benzene, and Z2 equals to 0.5, which is n-Hexane. The temperature that we used is 80 degrees Celsius, but this is just an assumption. For the partial pressure used must be more than atmospheric pressure, which is 101.325 kilopascal. So we assume 120 kilopascal. Since benzene and n-hexane make a geotropic mixture, and their separation by flash distillation methods at normal atmospheric pressure is impossible. The typical use of overall composition is zero point 0.5 for mostly test mixture.
General equations for gamma phi formulation of VLE. So from these equations, for every species of I, Yi will represent vapor phase mole fractions, while Xi will represent liquid phase mole fraction, and P will be the system pressure. Moving on, for the Pi saturation will be the vapor pressure at system temperatures, gamma I will be the activity coefficients, Phi I will be the ratio of vapor phase fugacity coefficients to saturated phase fugacity coefficients. So since the mixture solution is assumed at ideal states, therefore both I and I approach unity over 1. Hence, the above formula is simplified to equations below, which is known as Rhodes' law. So the assumption made during the calculation will be the mixture is ideal solutions and 100% separations, activity coefficient and fugacity coefficients of all species approach unity. Now I will introduce the questions. Our question is calculate the moles of liquids, moles of vapors, liquid phase mole fractions, and vapor phase mole fractions. For inlet streams, we simply let Zi equals the mole fractions of species I, and for the output streams, which having vapor phase and liquid phase, we let L equals the moles of liquids, V equals to moles of vapors, Xi equals to liquid phase mole fractions of species I, Yi equals to vapor phase mole fractions of species I. So our basis made for these projects is 1 kilomole per hour solution mixtures into flash column. From the mass balance, we are getting these equations. Since summation of Iyi equals 1, so we can conclude our calculations by using the equations located right below of this slide. From n-joint equations, we are getting the first equation seen in these slides. And from the bubble point and dew point, we are getting a second and third equations in this slide which calculates the pressures of bubbles and also the pressure of dew points. This slide shows the calculations of K values, and with the known value of Yi, we are able to calculate the Xi by using Yi divided by Ki.
So I'm going to present the first calculation. The first step is calculation of P set. We can obtain the constant A, B, and C from table B2 and substitute them into N2 equation. With the temperature of 80 degrees Celsius, we obtain the value of P set 1 is equals to 101.3287 kPa for benzene, and P set 2 is 142.5987 kPa for n-hexane. Next, calculation of bubble point and dew point pressure. We assume that x1, x2, y1, and y2 are 0.5 first. By using the formula, we obtain P bubble is 121.9602 kPa and P dew is 118.4701 kPa. Step 3 is calculation of K values. By substituting the P set obtained before and total pressure of 120 kPa, we obtain K1 is 0.8444 and K2 is 1.183. Step 4. Calculating V and L. From summation rule of Yi, we have this equation. By performing trial and error method, we obtain V equals to 0.5577 kmol per hour. Since L plus V equals to 1, so L equals 0.4423 kmol per hour. Next, since we have assuming Z for both substance is 0.5, by substituting the values we get new Y1 is 0.4623 and new Y2 is 0.5377. And using the new values, new x can be calculated. X1 equals to 0.5475 and x2 equals to 0.4525. Last step, since the summation of the composition is exactly 1, the values are valid.
Okay, next, as an extra information, our group has constructed a TXY diagram of the binary mixture of benzene and hexane at 120 kilopascal. From the figure shown here, region number 1 represents the superheated weapon, number 2 represents the subcooled liquid, while number 3 represents the two-phase regions. Also, we can obtain the extra information of the saturation temperature of both the pure n-Hexane and pure benzene from the red and blue color circles respectively. Okay, next, for the case of the overall composition of 0.5, 0.5, from here we can obtain the temperature range for flash separation to be occur, and our original selected temperature of 80 degrees Celsius is valid since it lies in this range. Another information we can obtain is that if at the process temperature of around 79.5, we could obtain the phase vapor with the maximum mole fraction of n-Hexane with around 0.58, while at 80.5 degrees Celsius, we could obtain the phase liquid with maximum mole fraction of benzene at around 0.58 as well. Okay, in addition, we also have constructed a PXY diagram of the same binary mixture at 80 degrees Celsius. As compared to the previous diagram, the only different things are the interchange of the region of both the subcooled liquid and superheated weapon. Also, we will obtain the information about the saturation pressure of both pure species instead of their saturation temperature. Okay, again, for the case of the overall composition of 0.5, 0.5, from here we can obtain the pressure range for the flash separation to be occur, and our original selected pressure of 120 kilopascal is valid since it lies in this range. Also, if at the process pressure of around 122 kilopascal, we can obtain the phase weapon with the maximum mole fraction of n-Hexane, which is around 0.59. At around 118 kilopascal, we can then obtain the phase liquid with the maximum mole fraction of benzene, which is around 0.58.
Okay, so today I'm going to talk about the process flow diagram, which is about this flash drum, where we have one inlet, which is we set as the basis, which is 1 kilomole per hour, with a composition of 0.5 for benzene, and also n-Hexane, and also two outlets. One is the liquid stream, one is also the vapor stream. Vapor stream is on top, and also liquid stream below. And moving on, right, this will be the mass balance equation where we find the composition and also the molar flow rate of each of the streams based on the basis that we set, and also the temperature and also the pressure condition that we set in before inside of the process flow diagram. And this is the summary of the table itself, where inlet stream and also the outlet stream data in terms of molar flow rate, and also the composition itself. And this is the energy balance table where we put down all the enthalpy change of each of the inlets and also outlets. And from the value that we get from table C1 and table B1, we're able to actually calculate all the enthalpy of each of the process flow. And with all the summary and also using the energy balance equation, we're able to get Q equals to 0.7050 kilowatt. And as a summary, right, this is the conclusion that we made where we set the basis 1 kilomole per hour, and also this is the mole fractions and also molar flow rate of each of the streams, liquid, vapor, and also we found out that actually the uh, amount of heat needed to be added, which is a positive value 0.7050 kilowatt into the stream in order to maintain a temperature of 70 degrees inlet and 80 degrees outlet. And that will be all for our presentation, and this is the reference that we actually use inside of this project itself. And thank you for listening.